This project is about physics-informed neural network modeling of a DC motor. Let's talk about modeling first. Well, accurate dynamic model is crucial for the purpose of optimization, control, and in maintenance as well. And we have three main modeling approaches. We have the white box, we have the black box, and we have gray box modeling. When we're talking about white box modeling now, it's also the same as the physics-based or the mathematical modeling of systems. While the gray box is the hybrid one, which combines both the black box, that is the data-driven, and the physics-based approach. So let's look at the level of complexity involved in these three modeling now. It is believed that as we move from the left to the right, the level of complexity increases, and that determines the type of modeling approaches that is being used, right, for most systems. And at the same time, when it comes to the kind of model assumptions or the insights we have about the systems, it's usually high on the left here. So it's believed that when we have good knowledge of the system, it's better to use white box modeling. And when the system is highly complex, it's best to use the black box approach. All right. So white box approach is based on first principles and it's difficult to apply when dealing with difficult systems. And the gray box or the black box is based on time series data, and we rely on the use of model structure, training or learning algorithm. And in these days of artificial intelligence now, we have different neural network models. And lately, researchers have been looking at physics-informed neural network. And that's what I will be dwelling much more on in this presentation. Physics-informed neural network. How can we combine neural network, that is AI, and the knowledge of physics in order to have a model that is more reliable? So, supposing perform an experiment, we are able to acquire input-output data, and we do data pre-processing. If we want to develop a neural network model, what we do basically is we inject the data into the system. We do what's called supervised learning, whereby there will be some inputs going into this neural network, and since we're going to have some desired output, we can then formulate a mean square error as the loss, and through back propagation we can update the weight and biases in this neural network. And at the end of the training, we can have a predictive model that can easily map the input and outputs that we've given to it during training. But for physics-informed neural network, it's a bit different, especially in this loss formulation part now. So instead of having just the mean square error alone, we can have the physics loss. And I'm going to talk later about how this physics loss can be integrated for a case study of a DC model. So at the end of the day, instead of having just a predictive model, with physics-informed neural network, we can have the unknown state of the system being estimated, and as well as parameters. So we have a video here.
Yeah, this is a DC motor, and I'm supplying it a PMW signal from MATLAB. As you can see, the motor is rotating around 200 revolutions per minute, and the controller we are using, the microcontroller in this case, is Arduino Uno, and this is the program from MATLAB. Okay.
All right, so let's look at the data that we collected during the experiment. So basically, we have the inputs and the output data. For the input, we have the PMW signal. You can see that in green here, pulse width modulation. For the angular speed, we have the red signal here, right? So we have the angular speed as the output we got through the encoder sensor. So we can see that the speed is not very stable, right? Because there is no controller in the system. But before we can even develop a controller, we need a good model, accurate model, in order to develop a controller, maybe simple ones like PID or fuzzy logic controller or LQR or sliding mode controller, whichever type of controller, even intelligent ones. Better our model, the lesser the effort we put in the control of this electromechanical system. All right, so this is the different neural network we tried. This is their architecture or the model structure. Yeah, we tried feed-forward neural network, we tried convolutional neural network, and we tried the long short-term memory. This is the prediction of the three models. We can see the prediction of the angular speed is very close to that of the actual motor. So we can see that yeah, the training loss was even small. The best result was gotten from when we used the feed forward neural network. So let's look at the physics based model. From basic knowledge of modeling a DC motor, you will recall that a DC motor has a mechanical part and it also has the electrical part. This is the mechanical part here, and this is the electrical part. To come up with this electrical part equations, we use Kirchhoff's law basically, and why Newton's second law is used in the mechanical part. So we can come up with an equation, a second order differential equation that gives the relationship between the output now, the angular velocity, and the input basically. And this can be used in the loss formulation as explained earlier for the physics informed neural network. So here I'm showing the result we got while we trained the physics informed neural network model. We can see the estimate is also good. I mean, the estimate of the angular speed, right, of the motor, right? And the aside that, we were able to estimate some of the parameters of the motor, which is something very good. We were able to estimate the inertia terms. We are also able to estimate even some other constants. Another thing aside that is that we're able to find what will be the armature current as the speed is changing. So this means physics informed neural networks is able to give us better results. I mean, more informative results than just using neural network. But of course, we need the physics knowledge. To develop physics informed neural network, the physics knowledge needs to be put into consideration. But if we're able to come up with the physics knowledge accurately and add this into the loss formulation, we can see that we can come up with a model that one will be reliable and two that can even give us some of the physics parameters that we are not sure about as demonstrated there.